Well, hello again out there in remote learning land. Today's hot topic, how to determine the shape of the Earth and how to prove it, right? Believe it or not, there is a group of people out there called a Flat Earth Society who still aren't convinced that the Earth is that spherical shape, but we'll talk about the evidence of that, observations you can make, and hopefully you can draw a conclusion as to what the shape is on your own. Anyways, prologue 16, 18. We'll go through those and be right back. Okay, so do you think the Earth is flat? How do you know? You've all heard the stories of ships that never came home, right? Never returned. So the idea is, well, maybe they fell off the Earth, right? And these old, pictures developed where the Earth must be flat. Because the only reason that a ship wouldn't come back, or probably anyway, is because it fell off the Earth. Lots can happen to ships at sea, as you know, right? Storms, tsunamis, all that stuff can certainly take out a ship. And who knows, maybe some of the crews got sick and couldn't make it back. But it doesn't necessarily mean the Earth is flat. So it was kind of a big conclusion to jump to, but you gotta understand, back in the day, of course, they didn't have all the information at their fingertips like you and I do. Okay? Sometimes, however, it's a matter of perspective. So if you're looking at this picture, and you say to yourself, well, what in the world is that? Well, if you remember from Living Environment, the bottom side of a leaf has these little holes in it called stomates. And that, I'm sorry, excuse me one sec. There are guard cells that open these little openings in the bottom of the leaf, right? And when you're zoomed in, you can see that, and it's beautiful, but it certainly doesn't give you a big picture. So you take a step back, and, now you can see the whole plant. Well, this gives you a little bit more of a worldly view. Certainly not far enough back to see the whole Earth, but you get the idea of what's going on. So take a further step back, right? Zoom out, if you will. And now you can see a bigger part of the Earth, and it still looks flat. And for most of history, this was the view people saw. Maybe if you climbed a mountain, you saw this view a little bit. Still looks pretty flat, so that would reinforce the idea of a flat Earth. But nowadays, of course, we have been able to zoom out even further, and by the time you get to space, there's no doubt we are living on a round Earth, right? Could it be a frisbee-shaped round? Well, we'll throw more evidence at you for that. But no doubt it certainly is a round shape. Okay? So how do we prove the Earth is not flat? This famous picture here is called Earthrise. And it was taken, from one of the lunar missions. And that's the Earth in the background rising in the moon's darkness there. Certainly giving you evidence of a round Earth as well. All right? But probably the best evidence we have, right, uncontestable at this point, would be evidence as far as photographs taken from space. Now, I know what you're thinking. They can be doctored. Yes, it's true, but certainly that is very good evidence. Okay, it looks perfectly round and smooth. It is not perfect, but it certainly looks it from a distance. All right? Then there was this whole scenario where as ships left, they seemed to disappear and sink. But then, of course, they came back a lot of times and they hadn't sunk. So what makes it look like it's sinking? Well, you must be going around a round surface. And these are different telescope magnifications. So as it gets further away, they use more power, so it keeps the size of the ship the same. But the ship still gets lower and lower on the horizon. And that's because it's going around the curved surface of the Earth. Okay? So get that in your notes. Earth has a curved surface. When a ship sails further away, the ship appears to sink. Okay? Then this is one of my favorites, right? During an eclipse, you get this beautiful phenomenon. Now, this is a lunar eclipse, not a solar eclipse. And you start with a full moon, and all of a sudden the moon kind of disappears, and then, of course, it comes back. When it disappears, you get this nice reddish glow. But that's not what we're focusing on in a second. Look at the shape of the shadow that occurs if you do a time-lapse sequence of a lunar eclipse. Son of a gun, that's a round shadow. Well, to make a round shadow, you have to be a round object. And guess which object is making that shadow? If you said the Earth, you're correct. That is the Earth's round shadow projected on the moon there, and that's why the moon went into its eclipse. Okay? During a lunar eclipse, the shadow of the Earth has a curved circular pattern. That's one of my favorites. Okay? So read this through. This is talking about more evidence using a star called Polaris, and we're going to talk more about that, of course. But the reason that you can navigate using Polaris, the North Star, is because Earth is round, and we'll talk more about that as well. So please make sure you read that. Okay. The altitude of Polaris changes in a definite pattern, and the angle of Polaris will turn out to be equal to the latitude of that person, but that wouldn't happen on a flat surface. That would be more of a round scenario. Okay. On a flat surface, the altitude of Polaris would always be the same. It would always be directly overhead. But that's not true. In Elmont, Polaris is about 40 degrees overhead. In Florida, it's about 30 degrees overhead. At the equator, it's 0 degrees overhead. It's on the horizon. So there's definitely more going on, and these are different evidences proving shape of the Earth. Okay? The true shape of the Earth, at this point, they have a great name for it. It's called a slightly oblate spheroid. And slightly, because with the naked eye, you can't see that it's a little bulged. It looks perfect, but it is slightly oblate. It's slightly flattened at the poles and a little bit wider at the equator. The actual measurements that have been taken support this as well, right? Circumference at the equator is this. Circumference at the poles is less, so it's a little bit flattened. And of course, you can do that with the polar diameter as well. Okay. This also affects gravity, and gravity is more evidence of this slightly oblate shape. At the North Pole, the Earth is, the surface anyway, is a little closer to the center because as Earth rotates, it bulges out on the equator. So the North Pole kind of gets a little flattened, and if you're closer to the North Pole, if you're closer to the center of the Earth, then there's a greater pull of gravity, and you're going to weigh more. So we use the funny example of Santa here. If he were simply to go to the equator, he would lose all this weight. No, it would be very slight. He would still look the same, but it would be a slight weight difference because now he's further from the center of the Earth. There'd be less of a pull of gravity, and he would weigh a little bit less. Okay? And that's all because of the Earth's rotation, changing the shape of the Earth a little bit into a slightly oblate spheroid, but it's still a sphere. Okay? Person will, at the North Pole, weigh a little more because the poles are slightly flattened and you're closer to the center of the Earth. And, of course, the opposite is true at the equator. Okay? So please make sure you get that all in your notes there. And then you get to your summary questions here. If you ever come across the one that says a true scale model of the Earth. Scale model means if you shrink something down, how will it look? Well, it's going to look almost perfect, like those pictures from space. So what's the most perfectly spherical thing you could find up here? Yeah, it's got to be the ping pong ball. Now remember, it is slightly bulged to the equator, but not with the naked eye that you could tell. Okay? The actual shape most correctly described as, well, again, this is actual. Okay? So that's the one you got to go with, the oblate, the slightly oblate spheroid. All right? These are those numbers that you just had in your notes as far as diameters and circumference. Based on these numbers, what does it support? Well, obviously that would have to be your slightly flattened at the poles, bulge to the equator, the slightly oblate spheroid. Okay? Last one here, if there were a gravity meter used at different places, what would that reading say? And hopefully you remember, if you're at the North Pole, you're a little closer, so you would weigh a little more, right? A little more gravity. All right, the reading would be higher at the North Pole than at the equator. Okay? So run through these. You should be able to answer all these questions at this point. If not, please go back and watch the lesson again. Pay attention to the details you missed. But you should be able to cite a couple pieces of evidence proving the Earth is not flat. I hate to say, contradict the flat earthers, but no, Earth is not flat. You should be able to describe the true shape of the Earth and some evidence for that. and tell me about that weight scenario, why you weigh a little more at the North Pole, a little less at the equator. All right? Awesome. I'll meet you back in a GC.